In this vodcast, we're going to take a look at freezing point depression and boiling point elevation. According to this graph, you can see that if this line here represents the freezing point of pure solvent, then that line there represents the freezing point if you turn it into a solution. It will lower the freezing point the more and more solute you mix into the solution. The delta T with the little b stands for boiling point elevation. This is the boiling point of the solution. This is the boiling point of pure solvent. So freezing point depression and boiling point elevation will occur when you take a pure solvent and turn it into a solution. Now, how much it changes is a function of the concentration. We have to measure in molality. That's the little letter m in this equation. We're going to measure the molality and multiply it by a boiling point elevation constant, K sub B, or a freezing point depression constant, K sub F. And nice people without social lives have calculated that for us. The point would be that if this is a constant, then the greater the concentration measured in molality, then the greater the change that you will see either in the freezing or the boiling point. And remember, we use molality because it's a unit of concentration that will not be affected by changes in temperature. So if we trot on over to the chart, normal boiling point of water would be 100 if it's pure, but the 0.51 K sub B, boiling point elevation constant, means that you will see a 1 degree Celsius increase if there's a 1 molal solution. You would see a 1.02 degrees increase in boiling point if it was a 2 molal, and so on. So what you will need to do is, as you do these type of problems, if they're simply asking you what is the elevation of the boiling point or the freezing point depression, they're just going to ask what was the change. If they say what is the new boiling point, what is the new freezing point, you would have to add the change in boiling point to the normal temperature and subtract the freezing point depression from the normal freezing temperature. So the change in freezing point is exactly the same equation, except we'll have different constants and subtract the change in the temperature from the normal freezing. A classic example of that is rock salt on icy roads will make the water freeze at temperatures less than 0. If your point is to try to make the surface of the highway safer for cars to drive on, driving in a slushy, watery mix is safer than driving on a solid, slippery, icy surface. And so adding rock salt will depress the freezing point of water. Notice that there are many different things besides water that can be solvents. And in any problem that you do on the 2 worksheets that accompany these vodcasts, you may need to refer to your textbook to find these tables if the information is not provided to you in the problem. So here's a very simple calculation of boiling point elevation and freezing point depression. Sometimes they'll just go ahead and give you the amounts, but this one at first looks like they're skimpy on the data. It says it's a 25% by mass solution of ethylene glycol, that's antifreeze, in water. So if you just pretend you have a big amount, like 100 grams or 1,000 grams, let's pick 1,000 grams. 25% of 1,000 would be 250 grams. So I'm going to say that I have a solution that has 250 grams of the ethylene glycol and 750 grams of water. I need to get molality. Moles of solute divided by kilograms of solvent. Well, the kilograms of solvent is easy. That's 750 grams expressed as 0.75 kilograms. The moles of ethylene glycol would have to be divided by their molar mass. And in this lovely, elegant equation they have here, they put all the conversion factors in, but I, for my brain, would have first taken 250 grams divided by the molar mass to get moles, and then divided by 750 grams of water turned into kilograms, 0.75. Here is the molality. Now that's pretty easy to do for both of those problems because now I have the molality in my calculator. I just need to go get the appropriate freezing point depression constant and boiling point elevation. Well, it told me that the solvent was water, So that's why you see the familiar 0.51 and 1.86 degrees Celsius per mole. That 2.7 degrees and 10 degrees are the changes in the temperature. Go back and read the question. Calculate the boiling point and freezing point. They don't just want the change, they want you to add the delta T of the boiling point to the normal boiling point and subtract the delta T from the normal freezing point. And now you will know the temperature at which that solution would freeze or would boil. The second type of problem you might see is the molar mass for freezing point depression or boiling point elevation, and this time we have to work a little bit harder. An unknown non-volatile non-electrolyte, well, I'm going to tell you that why we have to worry about non-volatile non-electrolyte in the next problem, but I can find out if it's an unknown what that substance is and also its molar mass if I have data for a known solvent. So it says we dissolve 0.25 grams of the substance in 40 grams of carbon tetrachloride. The boiling point elevation is 0.357 degrees higher than that of the pure solvent. You can break this problem up in a number of ways, but I think algebraically what I would first do is rearrange the equation, which was normally boiling point elevation equals the constant times molality. I could rearrange that to solve for molality. Now they told me it was carbon tetrachloride, so the 5.02 number came from a chart. I have the change in the temperature. I need to find out the molality. And notice that if you are good with your units, the correct thing will cause the Celsius to cancel out, leaving molal as the value that we need as the unit for concentration. Now you know that molality is equal to moles of solute divided by kilograms of solvent. There's the 40 grams of carbon tetrachloride. So I would automatically take any solvent and change that to 0.0400 kilograms. And I have the molality. So if I want to calculate for the number of moles, I simply would take the molality, 0.0711, and multiply it by the mass in kilograms. That will tell me the moles. You're almost there. The molar mass is expressed as grams of substance divided by moles. Well, they told me they weighed out 0.25 grams of the substance. I've got 2.84 times 10 to the negative 3 moles. So you simply divide grams over moles and you get the molar mass. So the molality, the freezing point depression or boiling point elevation, the constants, given the right information, will allow you to solve for the molar mass of unknown substances. This is a good point for me to stop this vodcast. The next mini vodcast will be for those problems that are dealing with ionic substances.